This problem is asking me to find the horizontal tangents to this curve right here. Call it a curve, it's a function. And by horizontal tangents, they mean they want the equation of the tangent line. So the slope at any point along the curve of this function is going to be the derivative. So now that I know the power rule, I can find this fairly easily. So I'm going to go y prime is equal to, well, I have 4x to the third. So I took my 4, I put it in front of the x, and I reduced my power by 1, minus 21x squared plus 4x. And then, remember, this is like 15 times x to the 0. X to the 0, anything to the 0th power is 1. So if I multiply 15 by 0, I get 0, and the slope of the constant disappears. So now I have a nice equation of my derivative, and I'm trying to find out, well, where is the slope horizontal? Well, we know when we have a horizontal slope is equal to 0. So I need to set this equation here to 0 to find where the slope is, where the horizontal tangent is. So I have 4x cubed minus 21x squared plus 4x is equal to 0. And when I'm working with any kind of polynomial, the first thing I want to do is I want to factor out all of the common monomials. So I have an x that I can factor out, which is nice, because now I have 4x squared minus 21x plus 4, and I have that's equal to 0. So I already know that one of my zeros is going to be x. So I'm going to have an answer where x equals 0. And now I need to find out, well, what values of x will make this expression 0? Luckily, it's a quadratic, because with quadratics, I can either factor it, but this looks like it's not going to be very easily factorable. I could try the surefire method of multiplying the a times the c, and I would get 16, and find out what factors of 16 will give me negative 21, and there are no factors of 16 that will get me negative 21. So that method isn't going to work. So what I need to do is I need to use a quadratic formula. In the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. And that gets me the zeros of any quadratic equation. So I always start with the discriminant, because if your discriminant is positive, you're going to have two real solutions. If your discriminant is 0, you're going to have one real solution. If your discriminant is negative, you're not going to have any real solution, so you can stop worrying about the problem. So I'm going to do the discriminant first. So that would be negative 21 squared minus 4 times 4, which is my A, times 4 again, which is my C. I like to use parentheses. It helps me from losing negative signs. So let's do the calculation on the calculator. So I have parentheses, negative 21 close parentheses squared. And I'm going to subtract, well, I can subtract 4 cubed. 4 cubed. And I get 377. So that equals 377. Positive discriminant, 2 real roots. So now to put it into the quadratic formula, I would have negative 21. Notice how the parentheses right here are keeping me from losing the negative sign right there. Plus or minus the square root, well, I already figured out the discriminant, so the square root of 377, all divided by 2 times 4, which is 8. So I'm going to just simplify that a tiny bit, and I have 21 plus or minus the square root of 377 divided by 8. So my function here is going to have horizontal tangents at 0 and at 21 plus or minus the square root of 77. 21 plus or minus the square root of 377 divided by 8. Now I'm going to backtrack a little bit. In this particular problem, I don't think we need to get the equation of the tangent line at both of those points. Well, actually, we could do that pretty easily, and I'll show you that in just a minute. Let's check it. Where I have a horizontal tangent line, I will have either a local minimum or a local maximum. My curve is either going to go like that, so I have a horizontal tangent line, or it's going to go like that, so I have a horizontal tangent line. So I need to look for minimums and maximums in the graph of my original function here. Well, it's easy enough to know where x equals 0 is, but I really don't have much of a conception of what that number really is, 21 plus or minus the square root of 377 divided by 8. So I'm going to plug it into my calculator, and I go 21 minus the square root of 377. And I'll hit enter, and I'm going to divide that by 8. So that is approximately, let's see if I can write this here without, it's approximately 0.198. And if I want to go to plus, I can just go back up here and copy that, enter, and then change it to a plus. Whoops, no, back here, hit it too many times. 2, 1, plus, hit enter, and divide that by 8. And that's approximately 5.05. So 0.198 and 5.05, I should have, so at 0, 0.198, and 5.05, I should have local maximums or minimums. Well, I'm going to try graphing this. I'm not going to do it on the TI. I'm going to do it on my Desmos calculator. And when I first plug it in, this is what I get. I get this function right here, but I can't really see very much of it. So I'm going to try zooming out a little bit and see what I can find. Oh, well, so I found something right there. I see there's a little thing right there that looks like it could be a horizontal tangent. And actually, I have 2 points there that they've marked for me. So I think I'm going to zoom in on those points a little bit and see what they are. So if I kind of zoom in a little bit, and a little bit more, and a little bit more, I can see now that my graph is actually doing a little tiny loop-de-loop here. So I have a local minimum right here at 0, 0.15. And I have a local maximum right here, sure enough, 1.98, and it's a little bit more than 15. So I have confirmed that that one is a 0, it has a 0 slope, and I've confirmed that that one has a 0 slope as well. What about this one here at 5.05? How am I going to check that one out? Well, I'm going to go back to my Desmos graph, and I'm going to zoom out and see if I can see something that looks like it might be a local minimum or maximum. And I know that I should, because this graph here with the highest power of 4 should have end behavior that is up, up. And here's up, and there's up, so I'm expecting that down here someplace it's going to turn around. So let's keep zooming out. It's pretty low. There it is right there. So I'm going to bring that up into the middle, and now I'm going to zoom in on it and see what I can find. Well, I'm getting a good look at the point, and if I hover over the point, 5.05, it marks it for me. That is my local minimum. So using the grapher, I've been able to confirm all 3 of my spots that are local minimums or maximums where I have a tangent line that is horizontal. As far as finding the equation of the tangent line, you know, I don't think I would give that to you, because to find out what the exact y value is at that point is going to be more calculations than it's really worth. Yeah, we could use the Desmos calculator and use their decimal approximation, but I'm not going to really put you through that. If I want you to find the equation of a tangent line, it would probably be something with integers, a little bit easier to do than this. Could I do this on the TI calculator? Could I do the same confirmation even though the graphing ability isn't quite as clear as on the Desmos calculator? Yeah, I think I could. And let's just talk about it a little bit. If you want to stop right now, you can. But I think it would be worthwhile discussing it so you get a deeper sense of how the calculator works and how you can work with it with your algebra. So I've entered the equation of our original function into the calculator, and I'm going to go zoom 6, and I'm going to get a graph of it. Doesn't really help me a whole lot, but I do know that the points I am looking for are at x equals 0, at x equals 0.198, and at x equals 5.05. Now, I also know that the highest power of this function is x to the 4th, which means that I'm going to have up, and behavior. I have a positive leading coefficient, and I have an even power. So I'm going to have up, and behavior. So I know if I have a little local maximum at 0, my function, it's going in this order from left to right, 0, 1.198, and 5.05. So I know that if I'm going to have a local maximum or minimum at 0, my graph has to be coming down at that point, and it's going to have to make a little turn up at 0 in order to have a turn again at 0.198, because I'm going to have two turns there. I have one at 0 and one at 0.198 in order for my graph to continue going down. Now that I know that down here, I'm going to have a minimum at 5.05, if in fact this is accurate. So I know that I'm going to have a minimum at 0, and I'm going to have a maximum at 0.198, and then I'm going to have another minimum at 5.05. It's the only way that I can do this and still have my graph have the up, end behavior. So let's use the minimum maximum features of the calculator. So I'm going to go second, calc. And I want to see if I have this minimum there for 0. So I'm going to search for a minimum. And my left bound has to be to the left of 0. So let's say, and I can pick any number. I'll go, my left bound is -1. And my right bound has to be to the right of the 0, but it has to be before I hit my maximum, because otherwise it might give me a different minimum. It has to be in the local neighborhood there. So I'm going to say my right bound would be at I can go 0.01. So I'm to the right of 0, but I'm to the left of 0.198. So let's hit enter. I don't want to make a guess. And sure enough, it gives me my minimum at 0. You know, sometimes they have these weird, the TI gives you this strange scientific notation thing that's really a 0. So that confirms the 0 at 0. Now let's look at the maximum at 0.198. So I'm going to go second, calc. Well, again, I want to find a maximum now, so I have to make sure it's a maximum. And if I didn't know, if I hadn't been able to draw this little graph here and know whether it's a minimum or a maximum, I wouldn't know what I was looking for, a minimum or maximum, and I might not get the right answers out of my TI calculator. But because I know enough algebra to be able to know that I have the end behavior of up, I can draw that little graph and know whether I'm searching for a minimum or a maximum. So I have a maximum at 0.198, so I'm going to make my left bound equal to a little bit more than 0, so I'm going to go 0.01. and I'm going to make my right bound anywhere in between this x value of 0.198 and my other value here of 505, which is a minimum. So I'll make my right bound, I know, I'll make it 4. And I hit enter. I'm not going to make a guess. And sure enough, it finds this minimum right here at x equals 0.198. Now all I need to do is find this maximum right there at x equals 0.18. All I need to do now is find my last minimum. So I'm going to go second calc. I want to find the minimum. And I want my left bound, let's say 4. And I want my right bound to be 6. And I hit enter. And I don't want to make a guess. And what do you know? I get 5.05 as a minimum. So we've just confirmed it many different ways. I'm pretty comfortable with this answer.